All right, so finishing up section 4.2, we're going to go into a little bit more discussion about asymptotes. Going to go a little bit more in depth. We talked about asymptotes a little bit when we were working with hyperbolas, and we will see them often with rational functions. But when we were working with polynomials, okay, just a general polynomial, there are no asymptotes. Okay, so polynomials don't have asymptotes. But in general, a definition of an asymptote is a boundary line. D-A-R-Y. For a given function. All right, so a horizontal asymptote is going to be a horizontal line, and it's going to tell us what's happening as x is getting closer and closer to infinity or negative infinity. So it's a boundary line as x gets closer and closer to either positive infinity or negative infinity. So the farther you go out on your x-axis, what is the graph doing? What is it approaching but won't cross? Okay, a vertical asymptote is where the domain doesn't exist. Okay, so when we're talking about horizontal asymptotes, these are horizontal lines. And it would be y equals something. A vertical asymptote is where x equals something. So if we're looking for vertical asymptote, we are looking for where the domain doesn't exist. All right, so just a couple things of note here. The graph may intersect a horizontal asymptote. For example, if I have a graph that looks like this, and I may have a horizontal asymptote out here, that this is not going to cross as it gets bigger and bigger and bigger, but over here it did cross the horizontal asymptote. That's okay. We're just kind of looking at what is happening as x is getting larger and larger, all right? But the graph will never intersect a vertical asymptote. And here's another one. It may intersect, and this is a new one we haven't talked about, oblique asymptotes or slant asymptotes. Actually, we did talk about these. These were the asymptotes that we used with hyperbolas, where we had an equation of a line. Okay, so that's where one place we will see a slant asymptote. They use the word oblique. That's kind of a technical math term. I will use the word slant asymptotes. So we have horizontal asymptotes, vertical asymptotes, and slant asymptotes. And that's kind of how I generally look at these. But slant asymptotes also looks at how x approaches large numbers. All right, so vertical asymptotes. If I wanted to find a vertical asymptote, I need to look for the zeros in the denominator. And this is going to tell me where my x values cannot, where we don't have an x value on our graph. Okay, so if I look at this, and this only comes from the denominator, doesn't matter what's on the numerator, but if I were to factor this denominator and have x plus 2 and x minus 2, I know that x cannot equal negative 2 and x cannot equal positive 2 because those are the zeros. Okay, so this is also equations of vertical lines, and they are my vertical asymptotes. Vertical lines at x equals 2 and x equals negative 2. On part B, I have a 0 at 1. So at x equals 1, I'm going to have a vertical asymptote. Okay. Part C. Now notice on part C, I can't factor this. Remember, we can't break up the sum of perfect squares unless I'm going to use imaginary numbers. But since we're using the set of real numbers, and here I would have my domain is all real numbers on this, there would be no vertical asymptote for this. Okay, so if I can't factor it without getting imaginary numbers, there's no vertical asymptote. And this last one, generally we're going to be factoring both the top and the bottom. We look at the bottom for the domain of the function, but here I would see I would have x plus 7 and x minus 4. And up here, x minus 3, sorry. That gives me 4x, 7 times negative 3 is negative 21. This would be an x plus 3 and an x minus 3. Now my domain on this one, I know that x cannot equal 7 and x cannot equal 3. But I only look for my vertical asymptotes in the most reduced form. So because I have a factor of an x minus 3 on top and bottom, I'm not going to have a horizontal asymptote. I'm sorry, vertical asymptote. I'm only going to have a vertical asymptote at x equals negative 7. In the next section, we'll talk about what happens here, and just to give you a heads up, if I have a factor on the bottom and on the top, I would actually have a hole in my graph at x equals 3. Okay, so I can't have a value at x equals 3. It's not an asymptote, but there is a hole there. All right, so now we're going to move on and we're going to look at finding horizontal asymptotes. When we're finding a horizontal asymptote or a slant asymptote, we have to look at the degrees of both the numerators and the denominator, and we're going to compare those degrees. So if the numerator is smaller than my denominator, which means the denominator is bigger, and here's an example, x over x squared plus 1. So that's my example here. We're comparing the exponents of the numerator and the denominator. So my bottom is definitely bigger, and if I were to go with very large numbers, essentially I would just be doing x divided by x squared. With a large number, if I add 1 to it, it's not going to make much of a difference. So this is really taking on the shape of 1 over x, which has a horizontal asymptote at x equals 0. So anytime my denominator is bigger, I'm going to have always a horizontal asymptote at y equals 0. So basically that's the x-axis. Okay, so this is horizontal at y equals 0. If my degree of the numerator is the same as the degree of the denominator, in this case my degrees are equal, okay, what happens is I'm going to look at the coefficients of those terms. So if I have an example, x squared over 2x squared minus 4. Okay, so really what I would have here as my x values get bigger and bigger and bigger, it would be approaching like x squared over 2x squared, where these x squares just kind of cancel out. So my coefficients of the top would be 1 and of the bottom would be 2. So I'm going to have a horizontal asymptote at y equals 1/2. Horizontal line through 1/2 on the y-axis. Okay, so no matter what my coefficients are, that's where I'm going to have a horizontal line. Then my third case is that my numerator is bigger than the denominator. Okay, so the top is bigger. And I'm going to clarify this. This kind of works if the top is bigger by 1. Okay, so an example could be x to the third minus 1 over x squared plus 2x plus 4. If this is happening where the numerator is bigger than the denominator by 1 for my exponent, then what I'm going to have to do is some long division, where we take the denominator and divide it into the numerator. So it would look like this: x squared plus 2x plus 4 into x to the third plus 0x squared minus x plus 0. And when I do this, I'm going to have an x here and x squared plus 2x squared plus 4x. That was a cube, by the way. Now I subtract the entire part. So this would be minus 2x squared. Negative 1 minus 4 is minus 5x plus 0. Then I'm going to multiply by negative 2. Negative 2x squared minus 4x minus 8. And subtract negative 5 minus negative 4 is negative 1x, and 0 minus negative 8 is plus 8. It doesn't really matter what the denominator is, or what the remainder is. This is going to be our equation in the form of y equals mx plus b. So this slant asymptote is going to be y equals x minus 2. And that's the equation of the line that would be a slant asymptote here. So looking at some examples down here, we're going to compare my denominators. So on part A, I have the top and the bottom are the same, so my degrees are equal. So in that case, I'm going to look up here. If my degrees are equal, Then I'm going to look at the coefficients of those degrees. So here's my equal degrees. My coefficients are 3 on the top and 1 on the bottom. So my equation of a horizontal asymptote is y equals 3 over 1, or y equals 3, and that's a horizontal asymptote. On the next one, I have the bottom is bigger, so when the bottom is bigger, we have a horizontal asymptote always at y equals 0. All right, so those were actually pretty easy ones to do. Looking at part C, I have the top is bigger by 1. So this one is going to be a slant asymptote. And to find out the equation where we have y equals mx plus b, I need to do my long division. All right, synthetic division doesn't work here because I don't have like an x plus something or x minus something. So I'm just going to do x squared minus 5x plus 6 into x to the third plus 0x squared plus 0x plus 0. X squared times x is x to the third minus 5x squared plus 6x. And I'll subtract here. 0 minus negative 5 is plus 5. And then 0 minus 6x is minus 6x. And then I'll estimate x squared times 5, that's positive 5, x squared, and I'm going to multiply 5x squared minus 25x plus 30. So when I subtract, I have negative 6 minus negative 25 would be positive 19x, and 0 minus 30 is minus 30. But the remainder doesn't matter. My equation is going to be y equals x plus 5. And that's my slant asymptote. Then we have one more like this in part D. My degree on top is a 3 over its second power, so I have 1 bigger on top. So top is 1 bigger. So that means I'm going to have a slant asymptote again. And if I divide x squared minus 2 into the top, x to the third plus 0x squared plus 0x minus 1. X squared goes into x to the third x times. This is x squared, this is x to the third minus 2x. And again, I'm going to line up my like terms. So that cancels, there's no x squares. So 0 minus negative 2 is 2x, and I can bring down the minus 1. And x squared does not go into 2x, so this is my remainder. That doesn't matter. So my slant asymptote is the equation y equals x. And again, slant asymptote. All right, so at the end of this section, this is what we should know. We should know how to find the domain of a rational function, and we should be able to find the vertical asymptotes. And both of these come from factoring the denominator. we should be able to find the horizontal and slant asymptotes. And we should know that there's 3 specific rules of looking at the degrees and comparing the degrees. And if the numerator is less than the denominator, I always have y equals 0 as a horizontal asymptote. If my numerator equals my denominator, I'm going to have a horizontal asymptote where y equals the coefficient, the leading coefficient, over the leading coefficient on the denominator. And if n is greater, my numerator is greater than my denominator, I'm going to have a slant asymptote, and we're going to use long division. Without looking at the remainder to write an equation in the form of y equals mx plus b. All right, so those are the important key concepts for looking at asymptotes. And in the next section in 4.3, we're going to take all of this information with the asymptotes, and we're going to put it together and actually do some graphing of rational functions.